All right, so we're going to do an activity in class tomorrow to cover the sampling distribution of a sample mean and really understand what the heck that means, these sampling distributions, because I had a lot of questions via email, and it was clear that we don't really understand what the heck they're talking about. But I'm going to cover a lot more of the kind of calculations and nitty-gritty with you guys in this video, so that way we don't have to waste class time on something that's pretty perfunctory and we've done before. So generally speaking, we talk about the sampling distribution for a sample mean. What we're going to have happen, I'm going to ignore this first example, we'll use that, is that if you take a sampling distribution of just, say, a sample of 1, what you're going to see is something that looks an awful lot like the original distribution. So in the example of tossing a die, which is what we'll do in class, the true distribution of outcomes, right, the true probabilities, 1, 2, 3, 4, 5, 6, should all be exactly the same, right? It's a 1/6 chance for every single thing. So that's what your plot should look like. And that's what you see in this first little drawing here, this first histogram. You can see if you toss a single die 10,000 times, you're seeing almost that flat, uniform distribution, which you expected to see based on reality or what the actual probabilities are. So if you were to actually figure out the mean for this distribution, if you were to calculate this up, and we can do this for our own as well, the mean should be around 3.5. It's just all these things added together divided by 6, which makes sense because if you think about a weighted mean, it's essentially what we're doing. Now, things change if you change your sample size. Like a single outcome, it will look like its population outcome with some added variability because it is a sample, right? But if we're talking about maybe a pair of outcomes and then averaging that pair, what's going to happen is it's going to be a lot harder to get 1 or a 6, because if we're talking about a pair of dice averaging to 1, that means basically we rolled snake eyes, right? The only way for that to happen is a 1 and 1 for the 2 rolls, which is a 1 in 36 probability, right? So that's going to be less likely than, say, rolling a 3 and a 5, or a 3.5, which is 1 and 6, 2 and 5, 3 and 4, right? 4 and 3, 5 and 2, and 6 and 1. That is a 1 in 6 probability. So this would be an average of 1. This would be an average of 3.5. So you can see 3.5 is the most likely thing, happening approximately a sixth of the time out of this 10,000 times. So hopefully we're starting to see what looks like our sort of unimodal symmetric distribution we're always hoping for. Now, obviously this doesn't have the bell shape of a normal distribution. We cannot use a normal distribution on this. However, if you were to say toss 20 dice and average them, now we're starting to see our bell-shaped curve, right? That normality. So that's what we're looking at when we're talking about the sampling distribution of a sample mean. Our sample means are going to come from a distribution that has the same average. You'll note every single place here, the average of 3.5 was the same. The middle values were similar for all of these distributions. What changed was the shape and also the spread. From our second distribution, we went from 1 to 6 for rolling a pair, and when we're rolling 20 die, we're now not getting anywhere near 2. Because in order for us to have an average of 2, we need a bunch of really, really low rolls, and that's a lot harder to get when you're rolling 20 things. So we're starting to see a couple of things happen as we increase the number of observations. One big thing, I'm going to go ahead and get rid of myself here in the corner. No, I made myself bigger. That's worse. It's terrible. I'm gone. Okay, good. A couple of things that we can see here. As we increase the sample size or our number of observations, we have more normality, right? We're starting to see that bell-shaped curve. And the other piece here is that there's going to be less spread. It's a lot harder to get an average that is outside of the range of reasonable averages when you're taking a larger number of observations. So that's what we're going to be using in the next page to do some calculations. So we have the central limit theorem. This is an important new idea that basically just says in statistical jargon, what we just confirmed, when you're taking a simple random sample of size n from something that is non-normal, so in the example of our dice, that discrete uniform, then the sample mean has a sampling distribution that is approximately normal. So it doesn't matter what we start with. Even if we start with something that's like on the first page where it's like this, it's all crazy, it will become normal if we're talking about the actual observations versus the sample mean, as long as our n is big enough. So that large enough is something we will chat about in a second. So in order for us to have this approximate normality, right, there are some assumptions that must be met. They should look very similar from part 6, nothing new here. The values have to be independent. We still need a simple random sample. Our simple random sample still needs to be no larger than 10%. So that way we don't have to deal with those without replacement issues. And now our rule of thumb has changed. We no longer have a P, a probability of success. So our rule of thumb is just that our n should be greater than or equal to 30. And this is only necessary if we started out non-normal. Something that is normal will be normal regardless. Something that is non-normal, that needs this rule of thumb to be met, so that way we can get the central limit theorem. That's our large enough. So our sampling distributions, this is our squiggly line notations. We just got 2 new ones. The mean of the sample means is the original mean. Kind of makes sense, right? If we're taking an average, we expect that average to be pretty much what the population's average was going to be. The standard deviation, we needed to put in something here that has it shrinking based on how our n getting larger, right? So it's the original standard deviation divided by the square root of n. This is something that is easily forgotten by a lot of students, that square root of n piece. We have 2 possible squiggly line notations. One has an n for normal, one has an an for approximately normal. The difference here is just whether or not you were told the thing was normal. So we'll see an example or 2. But really, if you have the word normal, this is where you are. If you don't have the word normal, and more specifically, I'll usually tell you something to imply that it was non-normal to begin with. So I'll usually say something like skewed. This means the best we can do is approximate normality. Now, nothing changes for us in terms of calculations or any of our work based on normal or approximately normal. The only thing that changes is the notation. And technically, in order to get normality, we don't need that big sample size because we don't have to use the central limit theorem. So that's really the importance of this top one here, is that this, you don't need n to be greater than or equal to 30. Here, we need n to be greater than or equal to 30. Otherwise, technically, we don't have this an. We can't do anything. Okay, so let's see our first sort of example of this in motion. So first question here just says, in engineering, weights of people are considered so that airplanes and elevators aren't overloaded, chairs won't break, and other embarrassing things won't occur. Men's weights are normally distributed with a mean of 173 and a standard deviation of 130. So we have our sweet keyword of normal. We also were told that men's weights have a mean of 173 and a standard deviation of 30. So let's look at our questions. First question asks, what is the probability? Which we know means that we're looking for an area under that normal curve, right? That normal curve that we know exists, that's centered at 173. And it says, what is the probability a randomly selected man weighs more than 180? So we're interested in a man weighing more than 180 or the area under the curve to the right of 180, right? That's what we're looking for. Notice here, we don't have any sample size. We're not talking about a sample mean. This is just an old school normal question. I mostly put this in here so we could see the two kind of side by side. So this question, if we want to find this probability, normal CDF, our lower bound, crap ton of nines, say we go off forever, our mean, and our standard deviation. So we just go ahead and calculate that. And this is when I wish I had gotten a calculator out before I started this whole process. So normal CDF. Nothing new here. This one, it looks like the probability is 0.4076. So about a 41% chance that a randomly selected man weighs more than 180. Makes sense. 180 is pretty dang close to that mean when you think about how big that standard deviation is. Now, to compare this, the second question here, B, changes things up. It says if 9, oops, that's not what I wanted. If 9 men are randomly selected, say to be in an elevator, now we have a sample size. This is very important. It says, what is the probability that their average weight is more than 180? So now we're not interested in just one randomly selected person from that normal distribution. We're interested in an average from a sample of 9 from that distribution being more than 180. So this is when we have to use all of this stuff up here, this mean and standard deviation, right? These two calculations, which are on our formula sheet under sampling distribution for a sample mean. So we can go ahead and do basically what we've been doing in a lot of the other parts, right? The mean of a sample mean is the real mean, so that doesn't change. The standard deviation of a sample mean is the original standard deviation divided by the square root of n. If we are taking 9 men and sampling them, it's going to be a lot harder for them to have an average that's further away from the true mean. So we have our standard deviation of 30 divided by the square root of 9, which looks to be 10. Now that we know what the heck our distribution is, that x bar follows a normal with 173 and 10, now that we have this new distribution, we can go ahead and draw our curve. We're still interested in the same thing, more than 180. My drawing looks nearly identical, and this is because I am lazy, right? I never take my standard deviation into account when I'm drawing this, but in the original we had a standard deviation of 30. Now our standard deviation is shrunk to 10. So this should be a much skinnier curve, which means it should be harder to have a probability more than 180. So we go to calculate this. Everything stays the same in this normal CDF, right? We're still 180, still crap ton of 9s. Our mean is still 173. The only thing that changes here is that standard deviation. And that is a very common mistake on that next exam, is to forget to change that standard deviation. So if we calculate that, we can see how that changes my probability. Now we're at 0.2420. So we went from a 41% chance that just one guy would make more than 180 to a 24% chance that 9 men would average a weight of more than 180. So it's a little less likely. Still likely though. It's still not that far from the average. So let's do one more of these. I'm going to do it in a separate video so you can check back for that.